Next, let's talk about escape speed. This is a silly concept in some ways because when you see a rocket launching from Earth, you never see it really reach the escape speed in terms of like escaping the Earth, like it has to be moving this fast. That's not the notion. I mean, you may see it reach the escape speed because it does accelerate to some large speeds, actually pretty close to these when it's out of space. But what this concept is actually is a theoretical construct, okay? And it is the minimum initial speed required, okay, that will cause it, whatever objects we're talking about, cause a body to move away from another body like a rocket moving away from the Earth from another body. And then that object will theoretically Friday kind of stuff. Come to rest only at a distance r equals to infinity. Okay? It's more horizontal. All right. So the idea here, the explanation that I'm going to give, parts, is that we have a body that leaves the surface of another body with an escape speed v, right? So at v, it has kinetic energy equal to 1/2 mv squared, okay? And therefore, okay, at that position, at that initial place, the gravitational potential energy is given by this. Right? When it reaches infinity, okay, and it stops, its kinetic energy is equal to 0, because speed at infinity is equal to 0. That's what we define as the escape speed. And u at infinity we also know is equal to 0. So the total energy at infinity is equal to 0 joules. For the conservation of energy, we know that 0 will be equal to the kinetic energy plus the gravitational potential energy. So really quickly here, some simplifying assumptions. We assume m is fixed, okay, and that m is the only body that's active. So assume m, the larger mass, is fixed. M is the only body we are considering. When you do that, we can derive the equation for the escape speed from what we said before, right? So what we're saying is that E total, right, is equal to 1/2 mv squared minus g big N little m all over r. Now this is all equal to, right, the gravitational potential energy and the kinetic energy at infinity. Okay, so when we set this equal to that, it's supposed to be equal to 1/2 mv infinity squared minus gn as r goes to infinity here, so we know that's going to be equal to 0. And we define that the infinity is also equal to 0, so this whole term is equal to 0. So the total energy is equal to 0. That's the Earth. So little b is our escape speed, and we solve it. When we do that, we get both these, we get the gravitational potential on the other side of the equation. Put the math here, we end up with this, the little m's are going to cancel out, okay, and then we end up with v squared is equal to 2g m all over r. Take the square root of both sides, we end up with this escape speed is equal to the square root 2g m all over big R. And that's our equation. Okay? I've got a couple of example problems here. What is the escape speed for Earth? Right? Plugging in values for these variables. Meeting the surface of the Earth. We end up with approximately 12 times 10 square meters per second, or in other words, 12 kilometers per second. The actual value is 11.2 kilometers per second. Other bodies are affecting the escape speed from Earth. Again, this is assuming it's only from Earth itself. If the sun shrunk into a black hole, okay, how large would it be? So what we're getting at here is that in the black hole, light itself cannot escape. Right, so our escape speed will assume to be the speed of light, which is nature's speed limits. Right, so nothing can go faster, so it's okay to say if light can not escape, right, that's the fastest speed we have to go, right, at all. Okay, so this would be the largest size the black hole can be. And we're going to solve for R. And we know that M times 10 to the 30th kilograms here. And when you solve for R, you get something around 3 kilometers. All right, again, I'm not showing the work there. You can solve for R. You guys can do algebra. I believe in the power